John Michell and black holes. In 1783, John Michell, an English natural philosopher and clergyman, proposed the existence of dark stars in a paper for the Philosophical Transactions of the Royal Society of London. With Newton's corpuscular theory of light, he reasoned that not only light particles could be slowed down by the gravitational pull of stars and that the escape velocity of a star could exceed the speed of light, making the star invisible, but also suggested a way to detect these stars by searching for binary gravitational systems in which one gravity source was non-bright. He incorrectly estimated these dark stars to have more than 500 times the diameter of the Sun. Pierre-Simon Laplace also suggested the same idea in 1796, independently of Michell. Michell also suggested that future astronomers might be able to identify the surface gravity of a distant star by seeing how far the star's light was redshifted, a precursor to Einstein's 1911 gravitational redshift argument. However, Michell cited Newton as saying that blue light was less energetic than red light, because Newton thought that more massive particles were associated with bigger wavelengths, so Michell's predicted spectral shifts were in the wrong direction. It wasn't until 1915 that Carl Schwarzschild published the first solution to Einstein's general relativity equations, which described the metric of black holes. Gravitational collapse was theoretically studied in sequent decades, and black holes were first detected in the 1960s. J.J. Thomson and energy-mass equivalence. In 1881, Joseph John Thomson, British physicist, thought about his discovery of electrons as balls full of charge, and applying Maxwell's equations, he concluded that moving electrons suffer from an electromagnetic force opposed to its movement due to the back reaction of their own field, just like inertial mass. This was a similar argument to Gabriel Stokes' hydrodynamics reasoning, who showed that the inertia of a body moving in an incompressible perfect fluid is increased. Thus, a moving charged body would apparently increase in mass through a so-called electromagnetic mass, and Thomson, together with others such as Heaviside and Lorentz, calculated the value of this electromagnetic mass to be 4/3 of the energy divided by the square of the speed of light, an equivalence of energy and mass. Hasen-Earl also arrived at the same effect with a moving tube with two end plates which emitted photons. Thomson also noticed in 1893 that the electromagnetic mass was dependent on the speed of the charged body. In 1905, Albert Einstein published the relationship between energy and inertia. In 1912, he published the famous equation of equivalence of energy and mass. G.F. Fitzgerald and length contraction. George Francis Fitzgerald, Irish physicist of the late 19th century, published a conjecture for length contraction in a short letter in 1889, in which he argued that if all moving objects were foreshortened in the direction of their motion, it would account for the null result of the Michelson-Morley experiment. He reached this conclusion by studying the way electromagnetic forces were affected by motion, and used equations that had been derived a short time before by his friend Heaviside and ideas from Hunt, considering the possible effects of motion relative to the ether on the forces holding the molecules of rigid bodies in equilibrium. Thus, he probably also thought that the intermolecular forces were electromagnetic. Hendrik Lorentz also developed a similar idea independently, leading to the Lorentz transformation in 1892, in which he introduced a second-order contraction effect to explain the experiment results. Later in 1905, Poincare realized that these transformations had the properties of a mathematical group, and Einstein published his principle of relativity, confirming length contractions while abandoning the idea of the ether. Oliver Heaviside, Gravitational Waves and Cherenkov Radiation. Oliver Heaviside, English self-taught physicist, worked on the analogy between electromagnetism and gravitation, published two papers in 1893 in which he defined a wave equation for gravity under the assumption that velocity propagation is not infinite. He considered how a gravitational field changes when the attracting bodies are moving and the field propagates at finite velocity, producing small perturbations in the orbital motion of the Sun. The non-detection of such perturbations set an upper limit on the speed of gravity, suggesting it was probably the same as the speed of light. He also theoretically predicted Cherenkov radiation in 1889 as conical wavefronts while reformulating vector notation of Maxwell's equations. Heaviside never accepted the implication of the predicted infinite mass in mass variation with respect to speed at the speed of light in electromagnetic effects of moving charges. Heaviside was correct in his belief of the possibility of superluminal motion if the medium is other than a vacuum, and his derived conical electromagnetic shockwave was similar to Cherenkov radiation. Later, in 1916, Einstein derived the quadrupole formula for gravitational radiation by solving the linearized field equations with the source term, and assumed their velocity to be the speed of light. These were detected in 2015, and Cherenkov radiation was first detected in 1934. F. Arthur F. Schuster and antimatter. Sir Franz Arthur Friedrich Schuster, German-born British physicist, coined the term antimatter in 2 letters in 1898, which would yield energy if combined with regular matter. He suggested that matter and antimatter repel each other, and hypothesized whole antimatter solar systems. Paul Dirac in 1928 predicted the existence of positrons, the electron's antiparticle, which were later observed in 1932. P. Gerber and Mercury's perihelion shift. Paul Gerber, German physicist of the end of the 19th century, worked on combining gravitation with a finite propagation speed. Other physicists realized in the 1890s that the use of modifications of the Coulomb inverse square law by introducing a velocity-dependent potential to represent the electromagnetic field applied to gravitation predicted perihelion advance for the two-body problem on the same order of magnitude as actually observed for Mercury. In 1898, he published an equation to derive the perihelion shift of Mercury by applying a theory of retarded potentials similar to that used in electromagnetism under the hypothesis that gravity propagates at a finite speed, which he calculated to almost coincide with the speed of light. Thus, the forces between two masses was to be corrected by a term that depended on the speed at which they were moving. Although inconsistencies were identified, and there was controversy on the way he derived the equation, the prediction was correct. In 1915, Einstein derived the exact same formula based on correct premises in general relativity.